Friends, this is the second lecture on the radiation heat transfer topic. In the last lecture, we were looking at electromagnetic radiation, its basic definitions, and tried to look at thermal radiation as a small, minuscule portion of the entire large spectrum of electromagnetic radiations. We understood the rationale behind the association between wavelengths and heat transfer. And then we also went on to define the quantities such as emissive power, and we also tried to look at the Planck's equation for emissive power as a function of wavelength, and the Stefan-Boltzmann law that relates total emissive power to temperature. And we also understood the Wien's displacement law. There were a few small errors in the numbers that I mentioned in the previous lecture, which I'll correct today when we go on. And we also defined quantities such as emissivity, which is the ratio between the emission at a given wavelength and temperature by a body, which is any surface, like for example the emissivity of these walls or the surface of your table, etc., can be evaluated as the emission per unit area at a particular wavelength at a particular temperature by that surface divided by the same quantity for a black body. So what fraction of a black body emission does a given surface emit at a given temperature and wavelength is what we call as the spectral emissivity, and this quantity multiplied by the emissive power integrated over the entire spectrum gives you the total emissive power of the ordinary body and the total emissive power of the black body. The ratio of these two gives you the total emissive power, total emissivity. So this is what we had looked at in the last lecture. In today's lecture, we'll try to formalize a few more quantities that need to be defined so that we can do calculations of radiation heat transfer. So one thing that we understood in the previous class is that radiation depends on wavelength. So if I have a surface emitting, it may be emitting different wavelengths at different energies at different wavelengths. So you can have a spectrum which is the variation of the energy emitted, let's say per unit wavelength interval d lambda, over the entire spectrum as a function of lambda. So E lambda as a function of lambda is called the emission spectrum. In the same way, the radiation also can depend on the direction. We can take a simple practical example. If you are walking, for example, in the evening sunshine on a floor which is well polished, you will find that the sunshine gets reflected and you get a glare because of the reflection of the sunshine from the floor when it is shining, when the sun is low, closer to the horizon. But at the same time, on the same floor, if you are walking during the middle of the day, the sunshine coming from overhead, this floor doesn't seem to be that glaring or reflecting, which basically means that it reflects practically most of the energy that comes onto the surface when it is coming at a more acute angle with respect to the floor, or more the larger angle with respect to the normal. But when it is closer to the normal, the reflection is less. So if I call a quantity called reflectivity, which is the fraction of the energy that is incident which is being reflected, then the reflectivity at smaller angles with the horizontal are more as compared with the larger angles with the horizontal. In contrast, metallic surfaces, for example, if they are shining, then they reflect more closer to the normal, but in the angles away from the normal, the reflectivity is lower. So this is one example of directional behavior of one of the radiative properties, which is reflectivity. In the same fashion, emission absorption can also vary with direction. So radiation is a quantity which is dependent on the spectrum, that is a wavelength, and also dependent on the direction. So these are two things that we will need to understand. So whenever we define radiative properties, we will need to define them as a function of direction as well as spectrum. And that is why the quantity that we define as the most fundamental unit of radiative emission should be taking care of all of these quantities. Okay. So that is another thing that we will be talking about today. Okay. So first of all, we will need to understand how we specify directions, right? So in order to do that, we will need to understand how what we call as a solid angle is defined. So let's move to the whiteboard so that we can take a look at that. Right. Now, in two-dimensional angles, when you define the angle as a radian, one radian is normally defined as, if this is the length of the arc dl from here to here, right? And if this is the radius r, then the angle theta in radians is defined as dl by r is d theta. Okay, so now this angle is in radians, and this is what we call as a plane angle. Okay, so this can be visualized like, you have a pizza and you want to slice the pizza to an angle theta, which will be equal to this length divided by this radius. And when you take the entire circle, this length is 2 pi r, and therefore that divided by r will give me theta varying from 0 to 2 pi. Okay, so a full circle is therefore 2 pi radians, and any other angle would basically be equal to the length of the arc divided by the radius. Okay, so that is how a plane angle is defined. In the same way, solid angle is defined with respect to a sphere. Okay, they look similar, the circle and the sphere, but imagine that this is the three-dimensional sphere. So if I take a surface, an elemental surface area of area dA here, then what it subtends at the center, this angle that is here is now no more a planar angle. This is called a solid angle. And the solid angle subtended there at the center is going to be equal to dA divided by r square. What is important is that this area dA that I am looking at should be normal to the radius, so we could call it as dAn in a similar way as this is dln, the length of the arc, which is perpendicular to the radius here, right? So this is dln by r, and similarly dan by r square would be defined as d omega, which is your solid angle. Okay, so the solid angle, just like your plane angle is measured in radians, the solid angle is measured in steradians. And a sphere has this total surface area integrated over the sphere is 4 pi r square, and therefore that divided by r square will give me a total of 4 pi steradians for the whole sphere and 2 pi steradians for a hemisphere, right? So this is the concept of solid angle. Let us take a look at it from the slide that we have here. So yes, there we go. So this is the definition of a solid angle. So suppose I take a small area on the surface of a sphere, and try to look at it from the coordinate system, then let us say this is the center of the sphere, and the radius of the sphere is this. Now this area can be looked up on the basis of a sector in the phi direction, which is the azimuth. So this sector going through the whole circle will be going from 0 to 2 pi, and we will take a quarter circle as an element which is rotated by d phi in the azimuthal direction to get this sliced volume. Now over that, if I look at a small segment which is given by a length r d theta here, if this is the segment in theta, where theta is the angle from the normal and the change in theta is d theta from here to here over this surface. Okay, so this side of the, if I call this a nearly rectangular surface, this would be r d theta, and what would be this? This would be, because the radius is this and this is theta, this is r sine theta, and r sine theta into d phi will be this. So this is r sine theta d phi, this length, and this length is r d theta. So the product of these two will be the DAN, which is r squared sine theta d theta d phi. Is that right? So if I define the solid angle as DAN by r squared, d omega is equal to DAN by r squared, for this particular surface, this DAN by r squared is d omega, and that DAN will be r squared sine theta d phi, and that divided by r squared, this r squared will then go off, so d omega would be sine theta d phi. Is that fine? So d omega is sine theta d phi. So this is something that we will use when we define the quantities corresponding to radiation. Now, so if I am looking at radiation emitted from this surface in this particular direction, that direction is given by the coordinates theta and phi, and the area, elemental area over which the emission can go through, is given by, on a unit sphere, it can be given as sine theta d phi. So that is your definition of solid angle. So if I am looking at radiation emitted in a particular direction, you say that it is emitted over a solid angle d omega in the direction omega, and that omega would be a function of theta and phi, right? So that is the thing. So if you are looking at radiation emitted over the entire hemisphere, then that will be radiation emitted over 2 pi steradians, that is, or d omega equal to, the omega equal to 2 pi over the 1/2 of the surface. That is, when you have an opaque surface emitting on one side, you will be emitting all through the hemisphere, and the total radiation will be the energy that is going through 2 pi steradians for an opaque surface. Okay, so that is usually the way it is counted. For emission, normally you look at only one side of the surface from where the emission goes. The other side is normally taken as unaffected by that for surface emissions. Then you take the reference geometry to be a hemisphere rather than a complete sphere, right? So that's how we calculate it. We'll look at it when we come back to it. Okay, so that is the first quantity that we wanted to define. The second thing that we wanted to define is what we call as radiation intensity. Okay, now when we want to define radiation, just like yesterday we looked at energy emitted at any wavelength, which is basically, we said energy emitted per unit area of the surface in a particular wavelength lambda is E lambda versus lambda, and we had some spectrum of that. In the same fashion, we would be like, we should be able to write E theta as a function of theta. So the energy emitted per unit area of the surface normal to the theta direction, and this basically is over your quarter circle that we looked at. If I look at the energy that is emitted in every direction theta, so this is theta equal to 0 and this is theta equal to pi by 2, from 0 to pi by 2, there is a possibility that the energy is uniformly emitted. That's one possibility, but it's also possible that there is a strong emission close to the normal, which is 0, and less emission on the other side, or there is a possibility that there is a strong emission close to the normal and less emission to the other side, and so on. So there can be a variation with theta. In the same way, over the plane from theta equal, let's say phi equal to 0 to phi equal to 2 pi, the amount of the energy radiated, the emitted energy can vary. So you can have phi going from 0 to 2 pi, and let's say E phi, the emissive power per unit area in that particular direction of projection. This can also have a certain kind of variation, right? So whenever we define radiation, the most fundamental quantity that defines it should be the energy emitted per unit area in a particular wavelength, in a particular theta and phi, right? So that is going to be the most fundamental quantity. So directional spectral emission per unit area is going to be the most fundamental quantity of radiation emission. So we will define that using what we call as radiation intensity. Okay? So the quantity that we define as radiation intensity this is basically directional as well as spectral quantity. So when you want to get the total energy emitted, you will need to integrate it over the directions, over the entire hemisphere and over the entire spectrum. So that is how we understand radiation intensity. So this is defined as I prime lambda E. Okay. So here the notations are that the prime stands for directionality, okay. So when it is independent of direction, then the prime disappears. Okay. So the emissive power E is actually integrated over the entire hemisphere, and therefore that doesn't come with a prime. The lambda in the subscript stands for spectral quantity. Okay, you remember the E lambda that we wrote. So it's a spectral emissive power, which is the amount of energy emitted per unit area from a given surface at a wavelength lambda, right? So that's your E lambda. In the same way, this intensity is also a spectral quantity. So it is going to be in a particular direction and at a particular wavelength. This E stands for emission. To distinguish it from the other aspects of radiation, which are absorption. So if I have a surface which is exposed to oncoming radiation, the oncoming radiation can have its own intensity. That will be I or I prime lambda I, which can be the incoming radiation at a particular direction and at a particular wavelength, right? So that's to distinguish that. So this I prime lambda E is radiation intensity of emission. So if I write it like that, then this can be written as dq dot, and that dot is important because it is the rate of emission. So it is the quantity in watts divided by per unit normal area in a particular direction will be dA cos theta. We'll understand why that with a diagram illustration. So this is the emission. So if we have a area which is emitting and in a particular direction, we are actually looking at the emission in that direction, normal to that direction. Okay. So that is why the quantity becomes, instead of dA, it becomes dA cos theta. So that is the quantity here. Then you have per unit wavelength in a direction, so that is d lambda, and per unit solid angle, which is d omega. So the radiation intensity is defined as the rate of energy emitted per unit solid angle per unit area of the surface projected normal to the direction of emission per unit wavelength and per unit solid angle. So this is the most fundamental quantity that is defined in radiation. Let us look at this with an illustration. So let us look at this slide. So we formally define radiation intensity of emission, that is I prime lambda E, as the rate at which, so the rate makes it the dq dot, rate at which radiant energy is emitted at a wavelength lambda in the theta phi direction per unit area of the emitting surface normal to this direction, per unit solid angle about this direction, and per unit wavelength interval lambda about lambda. So that's why I prime lambda E, which is a function of lambda, theta and phi, is given as dq dot divided by dA1 cos theta, and that is illustrated in this diagram on the right hand side, where if I am looking at the radiation emitted in this particular direction, which is theta and phi, then the projection of this dA1 normal to that direction is what you will be seeing there. So the area, per unit area, will be per unit of this area. Okay, so that's why you have a dA1 cos theta here, and per unit solid angle d omega, which can be written as sine theta d theta d phi, which is the definition of solid angle that we looked at earlier, and d lambda. So the basic definition of radiation intensity is I prime lambda E is dq dot divided by dA1 cos theta sine theta d theta d phi d lambda. So this is the basic definition of radiation intensity. Okay. Now coming back to the board work. Okay, so how do we relate this to the other quantities? Yesterday we looked at a quantity called E lambda, which is nothing but the energy emitted per unit area in a particular wavelength lambda. Okay, but this does not have the directional dependency, and therefore if I start with I prime lambda E, okay, which is dq dot divided by dA cos theta sine theta d theta d phi d theta d phi and d lambda. Okay, now in this, if I want to find out E lambda, which is actually dq dot by d lambda, is that correct? Everything else is gone. Then all of the rest, okay, and this is also per unit area, so therefore it's dA and not unit projected area. So dq dot by dA d lambda is what is going to remain. So this dA and d lambda are kept here. All the remaining quantities will have to go to this. So it will be I prime lambda E into cos theta sine theta d theta d phi. Okay, and that gets integrated over theta equal to 0 to pi by 2 and phi equal to 0 to 2 pi. So basically, if I take the radiation intensity and integrate it over the entire hemisphere, so if I have the radiation intensity going in one particular direction as I prime lambda E, if I integrate this radiation intensity over the entire phi range and the entire theta range, so that it covers this entire hemisphere, that is and because the projection direction is also rotating around the whole thing, this cos theta would also get absorbed there. So I'll need to integrate this whole thing on this side. So the spectral emissive power is related to your radiation intensity by this relationship. E lambda is equal to I prime lambda E into cos theta sine theta d theta d phi integrated over this. So in this case, suppose I look at E lambda B, which is the black body thing. So the same integral would work there, except that it will be I prime lambda B E, okay, into whatever quantities that is, the sine theta cos theta d theta d phi. And we know that black body emits the same amount of energy in all directions. So black body is known to be a diffuse emitter. it's not a stronger emitter in one direction than the other. It emits uniformly in all directions. So this becomes a constant. So it can come out of the integral. Then you will have an integral of cos theta sin theta d theta d phi. So if I integrate that, I'll find that this integral actually comes out 2 pi. How is that? Because this d phi integrated will give me 2 pi, and then you will have an integral over theta equal to 0 to pi by 2 of cos theta sin theta d theta. And cos theta sin theta d theta, what can it become? It can be written as, if I say sin theta is some t, then cos theta d theta is dt. So you get t squared by 2. So it is d of sin theta into d of sin theta. Okay, so it becomes d of sin squared theta by 2 is what you would get. And so if I integrate this, it actually gives me half sin squared theta and when I substitute these two limits, at 0 this becomes 0, and at pi by 2 it becomes 1, so it will become 1 minus 0, so it will be 2 pi by 2, which will be pi. Okay, so the integral basically will give me pi. So it will tell me that this relationship is nothing but pi times I prime lambda b e. Okay, so for not just black but any surface which has what I call as diffuse emission, that is, the emission is the same in all theta and phi directions, so that this becomes independent of theta and phi, then it is related to the respective emissive power by this relationship. Okay, so for any diffuse surface, E lambda is equal to pi times I lambda. Okay, so that's a thing. The prime will go away because it's the same in all directions, so it will basically be I lambda. So that is one thing. So when I say diffuse emission, then I prime lambda e is independent of theta and phi, then E lambda is equal to pi times the I lambda e. Basically the prime can be dropped because it's the so it's I lambda e, which because it is independent of direction, so it will become E lambda is equal to pi times I lambda e. So this is one relationship that you would get because of what I call as diffuse emission. So any surface whose emission does not depend on direction, it's actually a very rare thing to find because the black body is an ideal surface. Any surface which is real always has a directional dependence of emission, but the diffuse surface is only an approximation which sometimes we use in order to simplify the problem so that the directional integration can be avoided. Okay. So this is one thing. So in the same way, E, which is equal to integral of E lambda d lambda, this is something we looked at yesterday, from lambda is equal to 0 to infinity, is the integration that is required to be performed to get the emissive power. Okay. For a black body, this is EB is equal to integral of E lambda b, and this becomes equal to sigma t to the power of 4. And for any other object, it will be E is equal to integral from 0 to infinity of epsilon lambda E lambda b d lambda. Right. So this is the expression that we have. So this will be equal to epsilon times sigma t to the power of 4, where this epsilon is defined using this expression. So basically it is integral of epsilon lambda E lambda b d lambda divided by sigma t to the power of 4 will give me the value of epsilon, which is the averaged value of emissivity epsilon over the surface. If a surface has this E lambda, okay, which is epsilon lambda E lambda b, this epsilon lambda, if it is independent of lambda, that is, it has the same value at all lambda. So, for example, if I have E lambda if I write epsilon lambda versus lambda is a constant value, let us say 0.3. Okay, so then this is called a diffuse emitter. Oh, sorry, it's called a gray emitter. Okay, a surface is called gray emitter when its emissivity is independent of lambda and has a constant value throughout. Okay, so if this value is 1, then you get a black surface. Okay, if it is anything less than 1, it's a gray surface. What does it mean? A black surface will have a black body spectrum like this. This is E lambda b versus lambda. But if I have a gray surface which has a constant factor of this lower black, then you will get, this will be, so this is E lambda b and this is E lambda, and at any wavelength the ratio of E lambda to E lambda b will be a constant. That is what we call as a gray emitter. So a surface is gray if its emissivity, or rather, its emissivity is constant with spectrum, or its emissive power is a constant factor lower than the black body emissive power at that wavelength. So this is what we call as the gray emitter. So these are two gross approximations that we commonly make in order to make our calculations simple. Otherwise, the quantity E that we just wrote is equal to integral of E lambda d lambda. Okay, and this E lambda itself is an integral of I prime lambda E, okay, multiplied over cos theta sin theta d theta d phi. Okay, so basically this we said is dq dot by dA d lambda, and this is dq dot divided by dA. Okay, so the d lambda also goes here. So this is from 0 to infinity, and this is this integral basically is a double integral. Phi is equal to 0 to 2 pi and theta is equal to 0 to pi by 2, and therefore if I put these two together, this will be equal to integral over lambda is equal to 0 to 2 pi, 0 to infinity, and integral over phi equal to 0 to 2 pi, and integral over theta is equal to 0 to pi by 2 of I prime lambda E into cos theta sin theta d theta d phi d lambda. Okay, so that is your entire integral that will come. So if you want to find out the emissive power of any surface which is a general emitter which has variation in spectrum as well as direction, then you need to define its intensity as a function of theta, phi and lambda, and then integrate it over all of these quantities in order to get the emissive power. So this is something which is inconvenient, complex, and so we would like to find easier ways of doing it. So wherever it is possible, we try to make approximations of when the surface can be treated as gray or diffuse, or at least piecewise gray, piecewise diffuse. What do you mean by that? In the sense, suppose I can draw epsilon lambda as a function of lambda, okay, as just discrete values like that, okay, and it's 0 elsewhere, then it becomes a piecewise constant value of epsilon lambda. So over these regions we can actually take this epsilon lambda to be constant. So this can be written as epsilon lambda E lambda B. Okay, and that epsilon lambda being constant in those regions, you can use the fractions that we defined yesterday, f of 0 to lambda t. Those fractions can be used, and for this wavelength interval, and then this wavelength interval, and this interval, and then this interval, and then this interval, and this interval, we can use the delta f values and calculate the expression. The overall integral of E lambda b d lambda from 0 to infinity, this we know is sigma t to the power of 4. So this will basically be a sum of all of these fractions multiplied by sigma t to the power of 4. So that is an easy integration that we do. That is something which we said yesterday. In the same fashion, for the integrals over thetas and phis, suppose I can say this E theta as a function of theta can be written as, okay, it's some constant here and some other constant here between, let's say, 0 to pi by 2, or maybe more steps. So these constants can then help in taking this. Okay, this I prime lambda e can be actually this I prime lambda e for a black body is a constant. So if I can write this as epsilon theta into I prime lambda e, this epsilon theta being constant helps us to bring that out, and then the integral needs to be performed over only that region. This integral over that region can be performed not over the entire hemisphere, but over that region over which this is constant. So theta from, let's say, 0 to pi by 3 has some value, and pi by 3 to pi by 2 has another value. So this can be integrated in two segments, 0 to pi by 3 and then pi by 3 to pi by 2. Okay, so that is to take care of epsilon theta. So this is not E theta, this is epsilon theta. Okay, so epsilon theta is nothing but the E theta divided by E theta b. Okay, so that's the way it is defined. And similarly, we can also have with phi piecewise definitions. So let us say here that it emits, and here it doesn't emit, and here it emits and that doesn't emit, and these constants can be taken. So that kind of piecewise integrations then will simplify the total calculation. But if that cannot be done, then the problem becomes extremely complex and intractable. So for a first course of thermodynamics, or even at undergraduate level, typically the assumption that is commonly invoked is Gray diffuse, saying that we will ignore spectral variation, and we will ignore the directional variation of any emission, so that we can just treat this as a single quantity for the entire hemisphere, okay, and for the entire spectrum. So that is the thing that is commonly done. So the Gray diffuse assumption is something that we commonly use. So what we need to understand is that the Gray diffuse assumption is a very, very gross assumption, and there are no Gray diffuse surfaces that exist in reality. Okay, we always go with this premise that because the calculations are simpler, we learn to do this using Gray diffuse assumption. But when we need to calculate the real things, we will need to go into that complexity and learn to calculate the integrations as we have defined here. Okay. So with this, we have also understood that you would have emissivities as directional, spectral. Okay, so directional means in one particular omega, and if it is integrated over the entire hemisphere, it's called a hemispherical. Okay, so you call a directional emissivity or a hemispherical emissivity depending on whether you are looking at only one direction or uniformly over the entire thing. Similarly, spectral, if you are looking at only one lambda, and if you are looking at the entire spectrum integrated over lambda equal to 0 to infinity, then you get what is called total. Okay, so these are the terminologies that you have. So you can have directional spectral emissivity, which is defined as epsilon prime lambda. Okay, this is the energy emitted, in a particular direction in a particular wavelength, okay, by an object divided by the energy emitted by a black body in the same direction and in the same wavelength. So that is the definition of epsilon prime lambda. Similarly, you can have hemispherical spectral emissivity, which basically means that will be epsilon lambda, okay. So it has been integrated over the entire hemisphere, so it can be representative of the entire hemisphere now. So epsilon lambda is the amount of energy emitted in the entire hemisphere by a particular object, but at a particular wavelength lambda, divided by the amount of energy that is emitted over the entire hemisphere by a black body at the same lambda. Okay, so that is your hemispherical spectral emissivity. Similarly, you can have directional total, which is basically epsilon prime. So this is a quantity which is in a particular direction. You have integrated it over the spectrum from lambda equal to 0 to infinity to obtain the fraction of the energy emitted by the real surface as compared to a black surface. So this is what I call as directional total. So and the single quantity epsilon, which is basically hemispherical total, is integrated over the entire hemisphere as well as integrated over the entire spectrum. So this is called the hemispherical total emissivity. So what are the things? This is going to be equal to E divided by EB. Okay, this is going to be E lambda divided by E lambda B. This will be E prime divided by E prime. Oh, sorry, this will be directional, so it has to be intensity. So it has to be I prime divided by I prime B. Okay, so this is the intensity emitted by a particular object at all wavelengths in a particular direction, and this is the black body emission in the same direction, and this is going to be I prime lambda E divided by I prime lambda B E. Okay, so that is the definition. So these are the basic definitions of emissivity. So you can have 4 different categories of definition: directional spectral, which is the most fundamental, then directional total, which is integrated over the spectrum, and hemispherical spectral, which is integrated over the hemisphere, and hemispherical total, which is integrated over both the hemisphere and the spectrum. So that is the way in which. In the same way, you can define absorptivity, then you can have reflectivity, transmissivity, and so on. All of these quantities are related to radiation. The absorptivity is a fraction of the incident radiation that is absorbed, and that can be directional spectral, directional total, hemispherical spectral, hemispherical total. Similarly, reflectivity is the fraction of the amount of energy that came which gets reflected. Okay, so that can again be defined in the same way. And similarly, transmissivity is the fraction of the incident radiation that is transmitted through the medium, which can also be defined in the same fashion. Okay, so this is something that we will need to know from the basic definition of radiation intensity and the various other quantities that can be related to the radiation intensity through integration. And we'll also be able to define the relative quantities, that is absorptivity, reflectivity, transmissivity with respect to the incident radiation, and emissivity with respect to the black body radiation. Okay, so these are the quantities that we wanted to define in this particular class. So there is a lot of definitions, but there is an order to it, there is a simplicity to it. So I would advise you to go through the textbook and understand whatever I have said today in a comprehensive manner before we proceed with the rest of the course. In the rest of the course on radiation, we will be looking only at gray diffuse surfaces, and we will be deriving relationships of energy balance using radiation for gray diffuse surfaces. So we'll stop here and continue in the next class.